Hi, everyone. My name is Ali Hajimiri, and I'm going to give you a presentation today on a summary of how to use the time and transfer constants for determining the transfer functions and behavior of high-frequency behavior of circuits. Okay, so let's get started. So why are we talking about time and transfer, method of time and transfer constants? So the question is that it basically really boils down to what can you tell about a circuit without writing full KV, high frequency KVL and KCL and doing the analysis. Now, for example, if I show you the two circuits that we have like down below, if I ask you how many poles do they have, the transfer function from V in to V out, and how many zeros do they have? Can you tell by looking at them? Can you tell if the zeros are left half plane or right half plane, for example? And the other, more importantly, what parameters control where these things are, and that helps you kind of like determine how to modify the circuit, and make. In addition, the time and transfer constant method allows you to make quantitative measure predictions about the circuit, and also guides you through topological changes. This is something that's important in design in particular. Now, and the method of time and transfer constant in general actually allows you to calculate the transfer function to any degree of accuracy, including exact if necessary. And this is something that you may ask, so well, why do we need to do this if you have a circuit simulator that does this? Well, the circuit simulators are good at telling you numerically what something, if with a set of parameters, if it works or not. And you may even have an optimizer that may optimize a parameter, but they do not suggest topological changes. And that really has to come from understanding of what the primary parameters and what are the primary limitations of a circuit and where they come from. So that's what TTC is built for and intended to be used. And in this presentation, we'll go over that. So here's a little outline. We'll first talk a little bit about the general properties of the transfer function of a circuit with reactive elements, energy storing element. Then we'll talk about a first order TTC, basically a TTC for a circuit with one energy storage element. And we'll see that you can determine that exactly with 3 low frequency calculations. And then we'll also talk a little bit about the time domain response of that circuit. Then we'll talk about the method of zero value time constant. It is a known method, and you probably have seen some of that. We will go through a classic example of that you probably have seen. Then we'll see how that method gets modified if you have zeros, and how you can still use it and modify the time constants to get the good approximation and estimates of the behavior of the circuit using that. Then we'll talk about how, in general, the denominator coefficients can be determined. This is basically a time constant version of the Cochran-Grable method that we'll talk about. Then we'll see how that can be used not only to estimate the behavior of the circuit, but also with circuits with complex poles and complex poles, and how do you determine the natural frequency of resonance and quality factor of that using the time constants. Then we'll talk about the numerators, how to, in general, you can determine the numerator using a combination of time constants and what we call transfer constants, which are basically low frequency transfer functions which involve no reactive elements from the input to output. So basically, this can be low frequency gains or low frequency impedances and things of that sort. And then we'll see generally kind of that all of this leads to a very natural way of looking at the circuits like the ones we saw in the previous slide, and immediately being able to, very quickly being able to tell whether or not, how many zeros and how many poles and where they are and things of that sort, without even writing a single equation if you don't want to. And if you wanted to write equations, you can actually write them. It's very simple equations that allow you to determine it to any degree of accuracy. So let's get started on that. So let's start with basic properties of a transfer function. So the way we think about our circuit with an input UI and output UO is you can think about it as a box, which basically, in this circuit in general, let's say it can have n energy storing elements. It could be inductors and capacitors, reactive elements. And then let's say we have these elements, and the way we think about them is that we can think about everything else inside the box, the dependent sources, the independent sources, resistors, and everything that are not frequency dependent inside that box, and we take those n elements out and label them from 1 to n. And then you have an input UI and output UO. Now, this can be the two, for example, input voltage and output voltage of an voltage amplifier. Or, for example, it could be the current of a port and the voltage of the same port as the output, UO. And that would basically produce a transfer function, which would be an impedance. So it can be used for both impedances and admittances, for example, as well as direct gains, essentially, if you think about them. So this representation captures everything, not only just gain. Now, in general, for something like this, you can write a transfer function that it has the following form, meaning that you have a numerator and denominators, the set of coefficients Ai's and Bi's that are real coefficients. And this basically, it's a rational function if you have lumped elements like the ones that we have. Now, you can base, from the fundamental theorem of algebra, we know that this function, if each one of the polynomials in the numerator and denominator can be factored as a product of first order terms where the roots are either real or come in complex conjugate pairs, because you basically, or another way of saying that, you can factor it in as product of first and second order polynomials. And the roots of the numerator, of course, we know that they are zeros, and the roots of the denominator are called the poles. So these are reviews again. Now, and again, a little bit more review. So in general, if you look at an amplifier with a mid-band gain, which has basically a low frequency cutoff and a high frequency cutoff, what you have here is that you can break down, you can take the representation and rewrite it in a different way. So the same terms can be factored and written in the following form, which basically on the left-hand side, what you have, for example, here on the left-hand side, what you have is a basically set of what we call inverse poles and inverse zeros, the way we've written them. And on the right-hand side, we have poles and zeros. So the terms on the right-hand side are responsible for the high frequency behavior and the gain reduction, and the terms on the left-hand side are responsible for the low frequency reduction of the gain. And the way we think about this is that, of course, these are probably everyone's familiar with this, the regular poles and regular zeros. Or the amplitude response of a regular pole goes like this, the amplitude response of a regular zero goes like that. Now, the inverse poles and inverse zeros are basically a combination of, for example, an inverse pole is a combination of a zero at zero frequency and a pole at a frequency which is basically the frequency of interest. And what it produces is that essentially it produces a transfer function that looks like a mirror image of that of a regular pole. So what that does is basically effectively just produces something, and this is what we call inverse pole, and we show it with an X on top, with a bar on top, so that's the inverse. And inverse zero similarly has a mirror image, is a mirror image of the inverse pole. So this basically allows us to think about them in a more natural way if you want to. So the methods that we're going to talk about, there's historically have been developments, and some of these you may have heard about, like the OCT that was originally kind of like for capacitors only, and then a superset of that is ZVT, which basically determines the term B1 in the denominator. Both of them determine B1 in the denominator. OCT is only for capacitors, ZVT is both capacitors and inductors, but only determines the term B1 in the denominator. There's a Cochran-Grable method that determines all of the BI terms in the denominator. And then the generalized time and transfer constant, which subsumes all of these things and can determine all of the AIs and BIs in the transfer function. And in general, basically can determine the transfer function to any degree of accuracy, including exact. So let's talk about this. Let's start with the single energy storing element. Obviously, this will produce a first order system because there's only one initial condition that you can define for the system. You have 1 degree of freedom, so you will have only one pole. Now, in general, the transfer function of the system can be written as H of S with A0 and A1 terms in the numerator and the B1 term in the denominator. Now, you can show, and it's the proof of this thing can be found in the references that I'll show at the end, that it's basically the denominator B1 term is just what we call the time constant. And this time constant is basically the product for a capacitor one, for example, is the product of the resistance that's seen by the capacitor and the capacitor. And then for the inductive one is the inductor divided by that. And two quantities, H superscript 0 and H superscript 1, which basically what we call the transfer constants. And what are these three quantities can be seen better here. So these are three low frequency calculations. So that's H superscript 0. And remember, these are not powers, these are superscript. And essentially, superscript is the index. So this is one thing to will be helpful in all of the derivations, the equations that we'll show going forward in this presentation and this method, is that anything in the superscript is the index of the elements that are being infinite valued. So in this case, there's no elements. So basically, when you have 0, it means that nobody is infinite value. So H0, which is shown on the left-hand side, is basically when you set the capacitor or the element, it could be the inductor, to 0 value. Now, for a capacitor, if you set it to 0 value, it's an open circuit. And if the element were an inductor, it becomes a short circuit. So, but both of them are called what we call 0 value. So H superscript 0 is the transfer constant, basically we call it transfer constant because it has no frequency of dependence. So, which is the ratio of UO to UI when the capacitor is open circuit. Now, H1 on the right-hand side, which is shown with like the magenta color, is basically the same transfer, the transfer constant from the same input to the same output, but this time with a capacitor infinite value, which for the case, in the case of a capacitor corresponds to it being shorted, and for the inductor it would be an open circuit. So you can see that these two transfer constants are not necessarily the same, and they would lead to that. And then tau is the time constant seen, so time constant associated with the reactive element. So for example, if the reactive element is the capacitor C1, then the time constant is basically the resistance seen by C1 when all the sources are null, independent sources, not dependent sources, only independent sources are null, including UI. And you basically look at the resistance seen from those two ports, R superscript 0. And that times C is giving you time constant. And if you had an inductor, of course, the tau would be L over that resistance. So these three low frequency calculations are sufficient to determine the transfer function of any system with single energy storing element. So this is kind of a starting point, and this is an important one. And we can actually, let's look at an example and see, and also we'll see what other conclusions we can derive from this. For example, look at this simple common source stage. Now, in this case, we're just assuming only the single capacitor between the gate and the drain, and this is the CGD of the transistor. Let's call it C mu to have a single index to make life easier. And you have an input resistance R1 and output resistance R2. Now, if you wanted to determine the transfer function of this circuit, just a simple example, starting with this. So you have the three calculations, low frequency calculation. In the first one, the capacitor is open circuit. So this is essentially, in this case, the low frequency gain. So H0 is going to be negative GMR2, right? Because the input resistance of the gate of the MOSFET is infinity in the classical model. And then the second calculation is basically that of the time constant, the resistance seen from the viewpoint of the capacitor. And those of you who are familiar with the ZV-Turosity are familiar with this calculation. This is a simple one. It is basically R left, the total capacitance to the left of the resistance in this example, plus R right, which is the total resistance on the right-hand side, plus GM effective R left, R right. So basically you can see R1 plus R2 plus GM R1, R2 times C mu. So this is basically R naught, R0. And that times C mu gives you the time constant. And then the third calculation is also an interesting one, which is basically saying that, when you short circuit this circuit, this one, you should look at it. This is pretty straightforward from a small signal perspective, right? Because when you short circuit this, you see 1 over GM here, or RM. So basically that RM is going to be parallel with R2, and then you have a resistive divider between R2 and RM and R1, which is basically shown here. So this is H mu, which is basically the second transfer constant. And if you plug them into the equation, you can easily see that you obtain this transfer function, which is, this is the low frequency gain. You see a right half plane 0 and a single left half plane pole from the calculation. But you could actually tell this from, without even doing any calculation, that you have a single right half plane 0 and a left half plane pole. So how do we do that? So let's look at this derivation. So if you look at the original equation that we had for the transfer function, you can easily see that if you find where the location of 0 is with respect to the location of the pole, it follows this relationship. So the 0 is the H0 over H1 times the pole, the frequency of it. So therefore, if H0, the two time constants in H0 and H1, the two transfer constants have opposite polarities, it means that the 0 will be in opposite right half plane than the poles. And since we have a positive time constant, since the pole is in the left half plane, so we'll have a pole in the left half plane and a 0 on the right half plane. And that's exactly what happened in the previous example, if you look at it, because H0 it's an inverting amplifier. You have a negative gain. But when you short circuit this, you have a non-inverting gain, which is basically, so that the polarity of H mu and H0 are different. So, and therefore, what you see here is that basically they are in opposite half planes. And you can even not only tell that, but you can also tell whether the pole happens first or the 0 happens first by looking at the relative values of H0 and H1. So you can actually see that you can tell a lot by looking at the circuit, even without having to do any calculations for that. Now, the other thing that you can actually tell, which is quite interesting, is that you can actually write that transfer function, the first order transfer function that we wrote, and you rewrite it in the following form. So what you see here, you can rewrite it as two terms. The first term is a single low pass response, and the second one is a high pass response. You can think about it as a pole and an inverse pole. And each one of them, if you look at the step response, for example, will have its own step response scaled by h0 and h1. So you will have this response, 1 minus e to the minus t over tau u of t. And for the first system, so asymptotically reaching h0. And this response, which basically starts from h1 and asymptotically reaches 0. So your overall response of the first order system is always an exponential with a time constant tau, starting from h1 and ending in h0. So this is basically a useful thing to know, because if you know the h1, h0, and tau, you know everything, both time domain and frequency domain about this thing. And those three can be calculated from simple low frequency calculations. So for example, like now think about the situation that we had before, that h1 and h0 had different polarities, right? So in that case, what you have is that you basically start from one side and then you switch polarities, because you start from h1 and to go to h0, and this produces what we call, for example, an undershoot, even in a first order system. And an undershoot, as some of you probably already know, is basically a signature. If you see a time domain response with an undershoot, that's a signature of a right half plane 0. And that basically is something interesting to know and useful, and you can easily see that that comes out of this analysis. So the next step in this development is basically looking at what we call the zero value time constant. And this is a well-known thing. You may have seen it, but I'm just going to review it in the context, and then we'll go, because we were going to go beyond this, and just want to make sure that we have solid foundations in this. And basically, zero value time constants is a situation where you have now n elements, n reactive elements, and you're trying to determine essentially the term B1, the first term in the denominator. So basically, if you remember, the denominator was 1 plus B1s plus B2s squared, etc., etc. Now, and it basically says something simple, so that you can show that B1 is exactly equal to the sum of what we call the zero value time constants for each one of the elements. So each one of the elements, these are shown as tau i's to 0. So basically, for the first one, we have tau 1, 0, for the second one, we have tau 2, 0, etc., etc. So, and for the ith element, this time constant is essentially the element, let's say if there's a capacitor, the capacitor times the resistance seen by element i's, hence the subscript I. Subscript is the index of the element in question. When all other elements are zero valued, basically when you have a 0 up there means that nobody's infinite valued. So everyone else is zero valued, which means that for capacitors, they're open circuit, for inductors, they're short circuit, as shown here. And if it were an inductor, similarly, it would be basically that Li divided by that resistor. But other than that, it would be very similar. So you take this, so this is an important thing. So that B, that first term in the denominator, is exactly equal to the sum of all the zero value time constants, or ZVTs for short. Now, this is there are a couple of interesting points to be made about this. First of all, is that although this sum is equal to the sum of time constant, it's also equal to the sum of the negative of the sum of all the reciprocals of the poles. Because if you multiply those first order terms, you will immediately see that B1 is going to be sum of all the reciprocals of the pole frequencies. But the important thing is that there is no generally, there's no one-to-one correspondence between the time constants and the pole frequencies, unless they are uncoupled. You're dealing with an uncoupled time constant. And we'll talk about what an uncoupled time constant is later. But unless that happens, this time constant, there's no one-to-one correspondence. In fact, even their numbers are not the same. Because if you think about it, you could have more capacitors than you have, and hence more time constant than you have poles. For example, if you have a capacitive loop or things of that sort, or you have two capacitors in parallel, even if you think about it that way. Now, the other thing that's kind of like tells you that they can't be the same is that essentially the poles can be complex. They can have imaginary parts, but time constants are real. So obviously this cannot happen. And this is a common mistake that you see in many places. And sometimes even you can see it in some of the analysis here and there in textbooks, that it's an implicit assumption that's made that, you associate a time constant with a node or something like that. And you have to really understand what's going on. Otherwise you're making some incorrect assumptions there if you're making that assumption. And we'll see how it works. So now this exact knowledge of B1 can be used to make an estimate, an approximation of the cutoff frequency, high frequency cutoff frequency. So let's say you have a low pass system, and there are a couple assumptions that you're making here. One is that there are no dominant zeros and there are no complex poles. And if you have something like this, then the transfer function can be simplified to this form. And you will see that around the frequency of the omega h, around omega h, around the transition frequency, then this can be approximated as just the first term, because as you start from very low frequency, none of these terms matter, none of the S terms matter. And as you kind of increase the frequency, the first S term that starts mattering and having insignificance is the B1S term. And that therefore you can approximate it as this around the frequency omega h. And this is what you use for estimating the band. So basically you say omega h is approximately 1 over b1 because you're approximating it to the first order system, which is basically exactly, now b1 is exactly this sum. Now, this approximation always provides a conservative estimate, and this has been proven by Brian Honk, and there's a paper on that you can find, and if you are interested and see how it is, and it also gives you the bounds of that in that paper. You can actually see how accurate it can be. So let's start with this, and this is an approximation. So this basically leads to a very classical example, a design example that you may have seen, and it's a very good way of like thinking about design. So let's go through that. So let's talk about this classic. This is the one rendition of this design, it's classic design example, and you can make it more sophisticated and more complex, but let's just go through one version of that, which is this. So let's say you are trying to design an amplifier with a gain larger than the minimum gain. Let's say in this example is 50. You want to list a gain of 50. You have a source with the source resistance, in this case, like an R1 of 1 kilo ohm. And you have a load capacitance, in this case, let's say 150 femtofarad. And you're using a transistor. Let's say in this case, we've used the bipolar transistor. So those are the parameters of the bipolar. So you have the CJE, CJS, and CJC, and the tau F associated with the transistor. So the first design that you kind of start with is generally the common emitter. That's a gain stage. So let's say you are making something, let's say you bias a transistor at 1 milliamp, and you get a gain of, I don't know, you get a transconductance of 40 millisiemens, and you put a resistor of 2 kilo ohm there, you get an intrinsic gain of the amplifier of 80, negative 80, and then you have a voltage divider between the R pi at the input and R1. So basically that gain multiplies by that, which is this resistance times this GM here. So you get negative 80 times 0.7, and you get basically negative 57. So this satisfies the gain requirement, and then you can use it to estimate the bandwidth of the thing. But before we even do that, before we do any of this calculation, my question to you would be, how many poles and how many zeros does this circuit have? And how do we tell? How can we tell? Well, we can look at the circuit and see how many initial conditions can be defined for the reactive elements, right? So you can easily see that we have 3 capacitors here, right? But can we really define 3 independent initial conditions? In other words, if I set the voltage on capacitor C pi to 1 volt plus minus, and then C mu to 2 volts plus minus, then can I set the CL to any arbitrary voltage? No, because already it is forced by KVL to be at 3 volts because it was the sum of these 2 voltages. So I have only 2 degrees of freedom here. So I have 2 poles. Now, furthermore, the question is now, can we determine how many zeros we have? You remember that we have to look at the transfer constants to do that. So the question is that how many elements can we simultaneously infinite value and get a non-zero transfer constant? So looking at these 3 capacitors, in this case, all 3 of them are capacitors. So basically infinite valuing them corresponds to short circuiting them. So how many which capacitors can we short circuit simultaneously and get a non-zero output? You can easily see that there's only one capacitor, C mu, that you can short, then that will produce a non-zero output. Because if you short CL or C pi at any point, your output is basically, you'll get 0 output. And as a result, you can tell that there's only 1 0, because there's the highest order transfer constant that's non-zero is 1, the first order one. And you can also tell, as we discussed before, from the change of polarity, because you go from an inverting gain to a non-inverting gain, that this is going to be a right half plane 0. So in fact, we already know that this system has 2 poles and a right half plane 0. So, but let's apply the ZVTs to this circuit and see what we get from that. So one of the things that you see here is that if you can calculate the 3 resistances associated with it. So the resistance seen by C pi when the other 2 capacitors are 0 valued, basically they're open circuited, is R1 to the left and R pi to the right. Is that there's a parallel combination. The one that by C mu is similar to the one we discussed. The only difference is that R left, instead of being just R1, is now R1 parallel R pi, because we're using bipolar instead of a MOSFET. So you get the R left plus R right, which is R2, and then GM R left, R right, which is like in this case R2, I think is missing in this. I think it's a typo here. There should be an R2 after that last term for R mu 0. And RL, 0, which is the resistance seen by CL when the other two capacitors are infinite valued, is basically simply just R2, if we're ignoring RO in these cases. So, and of course, if we can calculate the numerical values, C pi's and CJS and CJCs for the GM of 40 millisiemens and current of 1 milliamp. So these are the values. So you can use this to calculate the 3 time constants in this case. You can see that we have 3 time constants and 2 poles. So you can easily see that they're not equal and even not in number. So you calculate these 3 time constants, and you can easily see that there's like the dominant one is the one associated with C mu. Because it sees a very large resistor, it gets multiplied basically by this quantity, GM R2, R1. This is a very large resistor, 57 kilo ohm. And it's dominated, and the second dominant one is the CL. You can see, in fact, actually, that your smallest capacitor is the one that is responsible for the largest time constant in this design. So it's not, there's not one-to-one correspondence between the size of the capacitor and its impact on the output. You have to look at what resistances it sees. So if you add some of these time constants, you will get the following expression. And if you go and calculate, use that to estimate the bandwidth, that's omega h estimate, you get this sum, and the estimate comes out to be 95 megahertz. If you actually run a simulation of this thing, so which is just shown here, so these are the body plots of the amplitude and the phase, you will see that you have a 3 dB bandwidth of 97 megahertz. So we have an estimate that's a little bit conservative, but it's pretty accurate. And then there's a second pole at 7 gigahertz. You can see it from the body plot, and a right half plane 0 that you can tell from the amplitude becoming shallower, but the phase continuing to go. So this is basically what you see. So now the classic design goes as follows. So basically you take the look at this and say, look, what can I do the next? So the good thing about the ZVTs, if you go look back, is that it gives you a guidance of where the problem is. And basically it guides you to a problem that's a well-known problem, which is that of the Miller multiplication. This capacitor, if the input of this capacitor goes up a little bit, the output goes down a lot. So it draws a lot more current than it normally does. So it appears like a much larger capacitor. And that's basically known as Miller effect, Miller multiplication. So to get around that, the classical solution again is to use a cascode where you bias the base of a second transistor up here. You have a common emitter followed by a common base. And now the question becomes, again, we have this stage, and if you absorb some of these capacitors like C mu of the second transistor gets absorbed also in this capacitor, and the C pi of it that gets absorbed into CE. So if you take all of this into account, and this is the kind of a simplified circuit associated with that, and we ask ourselves how many poles and how many zeros. Again, the same question. Again, how many for poles, you know, how many initial conditions. So you can look at these 3 capacitors down here that you can again see that you have a capacitive loop. So you can only define 2 initial conditions as we discussed before. And then you can define a third initial condition for CL. So you have 3 poles. And then how many zeros? Again, you see there's only still 1 capacitor. That's only C mu, shorting of which results in a non-zero output, and therefore, and you see that the polarity is also flipped. So as a result, you can see that you have a right half plane 0. So you can again similarly go and calculate the time constants, and this time you see that the tau mu went from 1200 picoseconds to 28 picoseconds. So we have significantly improved that to the extent that it doesn't matter anymore. Now, and now we are dominated by a different time constant, the tau L. Now, so this is a good thing. We've made an improvement, and if you look at the overall bandwidth estimate based on these time constants, about like 294, close to 300 megahertz. And if you actually go and look at the simulation result, you see that the bandwidth estimate is like the simulated bandwidth is like 330, 40 megahertz. And now we can also see that clearly that we have what we expected: 3 poles and a 0, a right half plane 0. And again, we have a decent improvement in the system. So if you wanted to improve it further, again, this provides, the ZVT provides an insight in the sense that you look at this and you say, okay, now the largest, you go after the second, now the largest time constant. You took care of the largest time constant, it has become pretty small. So you go after the second time constant. And what do we do about that? The problem is that you have a relatively large capacitance where you have a relatively large resistor, the load resistor of 2K. So you want to make sure that this CL sees a smaller resistance. And you can do that by having an emitter follower or common collector, a buffer stage, and introduce that. So you basically introduce a new stage. And you remember, each one of these stages we are adding is adding additional capacitors. We are really never taking any capacitor out, but as we are doing it the right way and making the appropriate topological changes, the quality of the bandwidth improves. And this is the kind of thing that the circuit simulator cannot tell you, because, you know, if you try to minimize things locally, parametrically only without changing topology, there's only limited amount of things you can do. So again, the same question, how many poles and how many zeros? So again, looking at this, you can see that you have 3 capacitors here, but you can only define 2 initial conditions because of the loop. And between CC and C pi 3 and CL, also you have another capacitive loop of 3 capacitors. So there are 2 more initial conditions there. So you have a total of 4 initial conditions. So you can expect 4 poles. Now, how many zeros? You can see now that there are 2 capacitors, shorting of which simultaneously can produce a non-zero output, which is basically C mu and C pi 3. So now you can see that they have 2 zeros. But now this is a bit interesting because shorting of C mu results in an inversion of the polarity, because this was an inverting stage, and shorting it makes it non-inverting. But shorting of C pi 3 doesn't produce an inversion because this was a buffer non-inverting stage, and it still remains non-inverting if you short circuit across it. So that means that you have 1 left half plane zero and 1 right half plane zero. You have 6 time constants because you have 6 distinct capacitors. And if you calculate them, you can see now that they are reduced, that the C tau L is significantly reduced. And you combine these time constants to estimate the new bandwidth. You have a new bandwidth estimate of like 550-ish or so. And you simulate this, you get a 720 or so bandwidth. So you see that it's coming, it's a conservative still approximation. And it is becoming a little bit more deviating more, but its bandwidth is significantly improving. And one of the reasons it's deviating more is that now we are violating a couple of those assumptions we were kind of like dealing with. One is that now you have complex pole, and the other one is that we have zeros here in the thing. And we'll see how each one of them can be dealt with going forward. So this is a classic ZVT example, and you can take it a few steps further and try to kind of like use to kind of go after the next time constants and things of that sort and see what you can do to improve it. But we'll stop here with that. But now the question is, so how about the numerator terms? How about the zeros? Now, can we determine that? And it turns out actually we can. And it's pretty straightforward and kind of simple expression. So the same way that B1 was just the sum of the time constants, A1, the first denominator, the coefficient of S in the numerator, is actually very similar. So it's the sum of the time constant, but each time constant is multiplied by its associated transfer constant, HI. Now, what do these transfer constants mean? What is H superscript I? H superscript I is the ratio of UI to UO to UI. This is a low frequency calculation. When all elements except for element I are 0 valued, and the element whose index is in the superscript, or elements that whose indexes are in superscript, are infinite valued. So in other words, if element I is a capacitor, it becomes short circuited, while everything else is 0 valued, as you can see. And you look at what is the low frequency gain from output to input under this condition. You can see that this is a different situation in general. And for each one of the time constant, it gets multiplied by that. So it's like more formal definition of that. Now, and this is very simple because now you can actually determine A1 as well. So in general, you can kind of get a better estimate, especially if you have 0 that matters, then it will show up in A1 and you can use it for estimation. Now, one of the things you could do is that you can notice that if you had a dominant term A1 as well as B1, so you're now, instead of defining it as a simple low pass filter, you have this response in the numerator. And A1 over A0 is simply, if you factor the A0, which is H naught, is going to be tau I0 times HI over H naught. And when you do that, you can see that you can improve your approximations by writing it as omega naught as B1 minus A1 over A naught from this term. So these are the first terms of the Taylor series, if you will. And you can, but now you notice that they are the sum over the same elements, and the tau I0 is common to them. So you can actually combine the sums and write it as sum of tau I 1 minus HI over H0. But now, interestingly, since both left half plane and right half plane zeros produce have the exact same effect on the amplitude response, the amplitude response of a right half plane and left half plane zero are exactly the same. And as a result, so you should treat them the same way. So it doesn't matter if the polarity changes or not. So that's why we have an absolute value here in the box expression. So what it means that you can take your time constants and modify them. You can define this modified time constant, which is shown here for some of your time constants, 0 value time constant. So your ZVTs get modified by this expression. And the interesting thing is that you only need to modify them if there's a significant HI. So you don't need to do it for everyone. You look at the HIs and see if there's any HI that plays a significant role or is large enough, and then you only deal with that and modify that time constant, and hopefully that will produce a more accurate result. So let's look at this and see where it takes us. So one of the things that you can see here, so this is another example. So this is exactly the same design example that we had before, the common emitter with the same values. Now, the only thing that's different is that now I've added a new capacitor C1 in parallel with R1. So if you look at this again and ask yourself the question about how many poles, how many zeros, you can see that you can only define 2 initial conditions still. So you have 2 poles, and then, but now you can also have 2 zeros because you can simultaneously short circuit C1 and C mu. So these are the ones that produce non-zero transfer constants, H1 and H mu, superscript 1 and superscript mu, that would matter, right? So the time constants are the same. So if you actually calculate the time, there's only one new time constant when you add this C1. So there's a time constant associated with the C1, which is the resistance seen by C1, which is the R1 parallel R pi. And if you calculate, it's a pretty darn big time constant. It's like 3,000 picoseconds and change. And if you look at the sum of the time constant, the bandwidth estimate you get from this is 34 megahertz if you just apply ZVTs. And you will see that from the simulation result that is significantly off. I mean, so substantially in error. And if you look at the non-zero time constant, there are only 2, H mu and H1, but H mu is insignificant because when you short circuit mu, you basically are killing the gain of the stage. So this ratio is going to be insignificant. So the modification to this time constant is insignificant. I just wrote it numerically, but you don't need to do it really. So the only time constant you really need to modify is a tau 1 associated with C1. And that gets modified by 1 minus H1 over H0, which is actually greater than 1, because now when you short circuit this, that voltage division at the input goes away. So you get the full gain of AD. And that ratio becomes 1.4. So this becomes negative. And this is the interesting thing, because the modified ZVTs are going to be actually different in the sense that they can be negative. So if you plug them in now, your estimate becomes 360 megahertz as opposed to 34 megahertz, so more than an order of magnitude higher. And if you look at the simulations, you have a bandwidth, a 3 dB bandwidth of 480 megahertz, which is a lot closer to 360 megahertz than 34 megahertz. So you can see that this system. And what's really happening here is that I chose this value intentionally. You can see this looks like a very particular value, because the way it was chosen is that basically we created a 0 and moved the 0 to put it on top of the first pole. So it was a pole 0 cancellation, which basically resulted in the second pole becoming the important thing and playing a role, because the first two are canceling each other and you don't see them, and the second pole is around these frequencies. So that's basically what was happening here, which is basically the classic standard ZVT does not see it and gets completely thrown off by it. But the modified ZVT with the first numerator terms does take it into account. Now, the other question, kind of like when we're talking about the zeros, they're kind of, I think it's good to think about the physical mechanisms of creation of the zeros. So there are several different mechanisms. So we are going to talk about 2 of them to provide some insight. One of them, which is common and is used, is that if you have a chain of amplifiers, and somewhere in the chain of amplifier, you have a capacitance and a resistor. And if you have originally you have this combination, but if you add a series resistance with your capacitor, you can actually create, you can modify your overall transfer function. So your transfer function after this modification, after addition of RZ, is the same as what it was before, multiplied by this. So you have actually, you can see that you can create a pole 0 pair that you can control them. You have degrees of freedom by controlling the values of RZ, R1, and CZ, where they fall. And this basically allows you to modify the response of the system. Sometimes it's used for compensation of amplifiers, this technique. Now, another thing that's very interesting and happens commonly in the amplifiers is basically the question of what happens when you have 2 signal paths. If you have 2 signal paths, what happens is that, so imagine this situation. This is kind of like a pretty abstract situation, but it happens quite a lot. For example, in a differential to single-ended converter, you see this often, but in a lot of other places. So imagine that you have 2 RCs that are driven by an ideal voltage source, R1, C1, and R2, C2. So in this case, the time constants are uncoupled. And we'll see the criterion for being uncoupled is that a time constant whose value doesn't change, whether or not you short circuit or open circuit any other reactive element, is uncoupled from everyone else. So if you look at this, you will see that you have two branches with gains of A1 and A2, and you do an ideal voltage addition of these two at the output. So what you have is that overall low frequency response of this thing, or the H naught, basically the first zeroth order transfer constant, is the sum of the 2 gains, obviously. Now, and interestingly enough, so each one of these have a first order single poled response, right? So each one of them is a low pass response. And you can see there's no 0 here, right? Each one of them has a single pole and no 0. When we say no 0, we mean that no finite 0. and we don't count the zeros at infinities, obviously. But the overall transfer function is the sum of these two. And if you write them and just like form a common denominator, you will see that you form a 0. And this is interesting and obvious because, you know, zeros should depend on the choice of the input and output and where the signals are, but the poles shouldn't because they're natural frequencies of the frequencies. And that's why all of the A terms have those H's, the transfer constant, but none of the B terms have those. That's some interesting pointers. But now you can see that when you have two signal paths, you create a 0 as a result. And this 0 is located at this location. You can actually calculate where it is, and it's basically given by this expression. Now, this expression is useful because it allows you to determine where it falls. So you can see that if the polarity of A1 and A2, the two signal paths have the same polarity, which is basically this in this situation, the 0 will fall between the two poles. And if they have opposite polarities, it will fall outside, and where depends on the relative size of that with respect to -1 or tau1 over tau2. And you can basically see where the 0 falls, depending on the choices of the ratios of A1 and A2 and tau1 and tau2. The interesting thing is that if you start with a second order system with two real poles and a 0, you can always do a partial fraction expansion and write it as sum of the two first order systems with a single pole. And this allows you to find a way to think about the time domain response of this thing, because then you can calculate what A1 and A2 would be in terms of the original poles and zeros. So we are doing the reverse here. And this allows you to calculate the effect of the time domain effect of the 0. So for example, if this 0 is between the two poles, in other words, basically A1 and A2 have the same polarity, you have two responses, right? You have a fast, large response and a slow, smaller response. So what happens is that your system gets close to its final value very quickly, but the overall response, being the sum of the green and the red, is going to take a long time to settle, and you will have the so-called droop. This is a problem if you're, for example, making a D2A, the output amplifier, because then the output of the D2A settles to a level close to the final, but it may take a long time for it to settle to LSP, especially if your LSP is small. So this is a classical issue when you have the 0 that falls between the two poles. Now, if you have a situation where basically the 0 is left half plane, and it's at a lower frequency than P1 or P2, basically closer than either of the P1 and the two poles to the J omega axis, lower frequency than either one of them. What happens is that you essentially have the sum of two responses, a fast response, a fast large response, and a slow negative response that's smaller. So what happens is that the system goes to the maximum value of the fast system, but afterwards, gradually the slow system brings it down, and you can have an overshoot. So you can see that actually you can have this kind of overshoot even in systems that do not have a complex pole. This is basically a system with two real poles. Of course, it's not a ringing system, but it's a single overshoot in the time domain response. So you have to be careful to identify the difference of these things. The other thing that's very interesting, and we kind of touched upon this when we were talking about the first order response, and similar things happening, is that now if the 0 is right half plane, which basically satisfies those conditions shown up here, what happens is that now you have a combination of a large slow response and an opposite direction, a fast response in the opposite direction, what's smaller. And this basically what happens in the beginning, the fast response, the red response dominates, so it pushes the system in the opposite direction, but eventually the green signal will bring it back in the right direction. And that produces an overshoot, which, like we said, is a signature of the right half plane 0 in this transfer function of the system. Okay, so great. And so if you want to think about all of these things and summarize it, this is basically the summary picture for all of those things. So you can see here that you have the different regions, and if your 0 is between the two poles, you will have droop. If it's here, you don't see any significant effect. If it's basically here, you will have an overshoot. And if you go in the right half plane, if the 0 is in the right half plane, you will have an undershoot. So that's great. So we learned something interesting about the denominator. But the question is that what else can we learn about the transfer function? Can we determine higher order terms of the denominator, for example, right? Now, the interesting thing is that the higher order terms of the denominator can be evaluated with a similar method. So we can actually use you can prove it in different ways. The original proof was done with basically looking at the cofactor matrices and all those things, but there's a simpler proof using that first order transfer function that we calculated for a single energy storing element system. And you can basically show it that B2, the second term in the denominator, is the sum of the two-way product of time constants. So the first time constant is the zero value time constant, if you calculate it. These are the ZVTs. The second one, tau ji, if you think about our notation, it should be clear what it means. The subscripts are the indices of the element in question. So for example, right now for tau ji, we are thinking about element J, for example, this element. And the superscript we said is the index or indices of elements that are infinite value. So it means that the resistance seen, so it's basically a time constant associated with this element, where basically the resistance seen across here, when element I is infinite valued. So what you can see here is that the element I, which was Ci, is infinite valued here, which you basically short circuited. And you look at the resistance here when also the input is null or zeroed. And you look at this resistance, and if it's an inductor, it would be L over that resistance. And if it's a capacitance, it would be capacitance times its resistance. So this would be the second time. So it's basically the sum of these things. And you only calculate it one way. You do Ij. So you don't do the other one. And there's this symmetrical relationship that's interesting because it gives you more than one way to calculate some of these products, which is interesting because you can pick the simpler one if you need to. And in general, basically, you can also do higher order terms. So the third order term and nth order term would be three-way products and all of things. And it may look very daunting to you. So, well, what am I going to do with these things? These are actually pretty easy to calculate because what happens is as you go to higher order terms, there are more capacitors that are shorted and more inductors that are open. So those time constants actually become simpler to calculate because a lot of those things are short circuited. So the complexity of the circuit actually becomes less, not more. So these are pretty straightforward to calculate once you get a hang of it. And this is basically the method for the denominator that Cochrane and Grable proposed in 1973. And Rosenstock wrote, initially it was written in terms of resistors, inductors, and capacitors. And Rosenstock wrote them in terms of time constants for the denominator. Now, the question is, what happens to the numerator? Can we do the numerator? And we'll get to that. But before we do that, let's see what else we can learn from this like higher order terms in the denominator. For example, if you have a second order system, if you want to approximate the second order behavior of the system, if you have peaking and ringing and things of that. So generally speaking, a second order response can be written in this form. Now, and you can see that there's a quality factor and natural frequency. The peaking in the frequency domain is approximately proportional to the quality factor. And the other thing is that we know that if quality factor is larger than 1/2, then basically what you have is you have a situation where you have complex poles, and if the Q is less than 1/2, you have two real poles that can factor. Now, if you look at these two, you can see that the quality factor, which is 1/2 damping factor zeta, is basically square root of B2 over B1. So what you can do, you can estimate B2 from the dominant time constants, and B1 you've already calculated from ZVT, and that gives you an estimate of the quality factor. And if natural frequency is basically also can be estimated from 1 over square root of B2. So this is an example, right? So here's an example. It's a simple example, a little bit of a contrived example, but it's an interesting and good example in the sense that you have a circuit which basically is a follower driving a capacitive loop. Of course, you can have a current source here to bias it, so we are not showing that. And then you have a Vin, a source resistance of 2 kilo ohm, and you have a C pi and CL. You're not including C mu in this calculation. So you have two ZVTs, two zero value time constant, tau pi 0, which is the resistance seen by C pi, times C pi, which is R MC pi, and tau L0, which is the resistance seen by CL times the CL, which is again tau R MCL. And then you need one more second order time constants for this calculation, which is basically tau pi L, which basically means the resistance seen by C pi when CL is infinite valued, in this case short circuit. So if you short circuit this, you will see that to the right, you will see the gate of the transistor because this becomes grounded. And to the left, you will see R1. So you basically have R1 C pi. And if you use these, basically the expressions are pretty straightforward. So B1 is the sum of these two zero value time constants as we knew. And B2 is this two-way product, tau L0, tau pi L. And you can see that it's basically given by this expression and it has this numerical value 250 picosecond squared. Now, if you calculate the quality factor based on square root of B2 over B1 as these, you see it's basically square root of 10, which in dBs would be 20 log of square root of 10, which would be 10 dB. And you can see that simulation basically shows a 10.2 dB peaking, which is very close. And if you look at the natural frequency, you would estimate it to be 10 gigahertz roughly, and it's I think at 9.8 gigahertz. So it's pretty close. And this is a way to see if you actually, the ZVT is also being violated, and if there you have complex, the assumption for the ZVT is being violated, and if you have complex poles that you have to worry about. So now let's go to the higher order terms of the denominator. They're numerators, sorry. So the title should say numerator, not denominator. So that's actually a typo. And so it basically, we are talking about higher order numerator terms, AIs. And this is basically, it's a very similar expression to B2, for example. Like for B2, we had tau I0, tau ji. But now we have each one of them gets multiplied by Hij, which is a second order transfer constant, meaning, and the way it's calculated is shown in an example here. So both element I and j are infinite valued. And in this example, element I infinite valuing is capacitor short circuited, and the element j being infinite value is the inductor being open circuited. And this sum, and then you can get higher order sum, which are exactly the same as B1s, except for the fact that they can each multiply by the nth order transfer constant. And you can see from this one very easily that for the numerator, the highest order non-zero term, highest order an, that's non-zero, is determined by the highest order Hij, Hij, whatever, or however many indices you have, that's non-zero. And that's why the criterion for the number of zeros in a transfer function was the maximum number of elements that can be simultaneously infinite valued to produce a non-zero response, because that would give you the highest order non-zero Hij, and that would produce basically what you have, the number of zeros that you have in general. So it's interesting. There are actually, so we did talk about this corollaries. The first one is the one we just talked about. And the second one is that basically in general, because, so there can be situations where there are clusters of time constants that are coupled. There can be a single time constant that's uncoupled from the other ones. We briefly talked about that. And the way you know it is that you can see, for example, for the single tau3, if the resistance, if the tau3 doesn't change, regardless of how you short circuit or open circuit. So for element 3, let's say it's a capacitor, right? C3. And it doesn't matter whether or not you short circuit or open circuit all the other inductors or capacitors, and this resistance seen by this C3 does not change, then this time constant is what we call is uncoupled, which basically means that this term can be factored out of the big polynomial separately. And in that case, there's a one-to-one correspondence between that time constant and the pole frequency. Now, there can be a situation where two time constants are mutually coupled, but they're uncoupled from everything else. So for example, elements 1 and 2 can be coupled to each other. So basically between the two of them, you can have a situation where you have a, the time constants are coupled, meaning that shorting or opening of one affects the other one. So tau 2,0 is not, for example, equal to tau 2,1 or something like that. Basically, they would not be equal. That's as for example. But shorting or opening of other elements, element 3, 4, 5, 6, does not have any impact on whether or not these guys are going to change. So this group are coupled. Basically, it's like a second order polynomial that includes all of these taus and can't be factored purely in tau 1,0 and tau 2,0 terms. It would involve tau 2,1, 2, but they are uncoupled from everything. So basically, the space of the time constants and elements is partitioned into blocks that can be uncoupled from each other. And this is also important when you're thinking about evaluating circuits. So with that, let's do a few examples just to see how these things work. So for example, let's say we are given this circuit, this circuit with 3 energy storage elements, bandpass filter, I'm just telling you up front, but, and we are trying to determine its transfer function exactly using the TTC. So the time constants are basically shown here. You can verify them yourself. So the first line is the 3 zero value time constant. So for example, let's give you an example, like C1, the tau 1,0. What is the resistance seen by C1 when L2 and L3 are zero valued? When they're zero valued means that they're short circuit, they're inductors, so they're short. So basically on the right-hand side, you have short to ground. So all the resistance you see is one on the left-hand side, which is R. Also, you're nulling the source. So you can see RC1, right? Or for L2, for example. So L2, you can see that to the left, if the capacitor is zero valued, it's open circuit. And to the right, if the inductor is zero valued, it's short circuited. So again, you see R, so you see L2 over R, and so on and so forth. And then, for example, but now if you go, for example, to tau 2,1, is the time constant associated with CL2 when C1 is infinite valued. right? The element 1 is infinite. So if it's infinite value, it's short-circuited, and on the right-hand side, this is still 0 value. So both of them are short-circuited. So you have an R on the left and R on the right. So you have an R over 2. So it's L2 over R over 2, which would be 2L2 over R. And so on and so forth. You can calculate these one. And this last one, I'm just going to do it, for example. So let's say tau 312. So this is the resistance seen by L3 when both C21 and L2 are infinite valued, meaning that C1 is shorted and L2 is open. So basically you see the R on this side and R on that side. So you basically see 2R in series. So the resistance seen from L3 perspective is 1R here and R here, 2R. So it's L3 over 2R. And now, so these are the time constants. And if you look at the transfer constants, you can easily see that there's only one transfer constant that's non-zero. It's basically when capacitor C1 is shorted and inductor L2 is opened. So basically means that C1 and L2 are both infinite valued, which is basically H1, 2. And in that case, you just basically have a resistive divider because L3 is still 0 valued, so it's shorted. And you get a 1/2. And then if you plug them in, you can easily see the transfer function is given. Now, this is another example. So here's basically a notch filter with two conducting an LC. And again, the time constants are given here. So these two are the 0 value time constants. This is basically the product of the 0 value and the second order time constant. And you can easily see that these are the case. You can just like verify them yourself. And the transfer constants are interesting because actually 3 out of the 4 transfer constants are non-zero. So you can see that the highest order transfer constant here that's non-zero is second order, which basically HLC, which basically says that all 3 of these are the same. And this is interesting because when all 3 of them do not change polarity and do not change value, that basically means that you are dealing with a situation where you can have, for example, J omega, zeros on J omega axis. And you can easily see it. If you plug it in, you can see that you have 2 zeros on the exactly on the J omega, neither on the left half plane or right half plane. And then you have 2 poles, and then you have a quality factor, which you can easily determine from that square root of V2 over V1, basically square root of this over that, which is exactly what you have on the right-hand side. So this is another example. Now, if you go back to this, like the 2 examples that I showed at the beginning of the lecture, the first few slides, this one we already did. We looked at this and we talked about this when we were doing the example for the ZVT. And on the left-hand side, if you look at this circuit, let's determine how many zeros and how many poles we are expecting to see. So we have 6 energy storing elements here, but we can see that you have a capacitive loop here between C2, C4, and C5. So basically you can only define one fewer initial condition. We don't have a purely inductive node, so we can define all the currents. So we have 5 initial conditions that we can define. So we have 5 poles. Now, how many zeros do we have? Well, look at this. So what are the max elements that we can infinite value and get a finite output, right? So if you infinite value L3, we are good because it opens the L3, so it doesn't short it to ground. L6 the same way, and C4 as well. The other elements will short circuit it or open it from the input, or detach it from the input. So you have L3, C4, and L6. So basically H346 is the largest transfer constant that's non-zero. And that would basically tell you that you have 3 zeros. And in this case, since the polarity is not changing in any of these cases, there's no inversion involved in this, you know that it's going to be left half plane. So you have 5 left half plane poles and 3 left half plane zeros in this example. And that's basically how you know a lot of things about this. So a little bit of the kind of historical overview for those of you who are interested about the development and when these things happened kind of at different times, and they were kind of generalized, and there were alternative paths like the Middlebrooks N-element theorem, which is different from what we are using here. And then the generalized TTC that we're talking. So if you are interested in more details of this thing, there are several resources. There's that paper on the top. You can look at it, which kind of goes into the proofs of these things and also shows some of more examples. If you want to see more examples, you can look at this document here on chapter 4. There are a lot of examples on that. And also there are several views that go into details of these examples and a lot more other examples about this when you look at these things, if you have more interest. And with that, I can stop here, and thank you for your attention.